Welcome to solverfy.
This is the answer to Chapter 16, problem number 33 from the Smith Organic Chemistry textbook. And in this problem, we are asked to draw all reasonable resonance structures for each of these four species that were given. And so in an effort to cut down on the length of time this video is going to take, I went ahead and just drew out sort of like basic skeletal structures for each of these species. Because the carbon connectivity is not going to change, right, in a resonance structure. It's just going to be the positions of electrons, including, double bonds. And so I've drawn out all the basic skeletal structures that we'll need, and I am going to show movement of electrons in blue, and then I'll fill out charges and double bonds on these structures as we go along. Okay, so for A, we have this carbocation attached to an aromatic ring. And so we can start to move some of the electrons of the aromatic ring around. And so that's going to give us a double bond here. Neither of our other two bonds in the ring will be affected. And so our carbocation is now situated here. Okay, so there's our first resonance structure. And we're just going to continue moving the electrons of this ring around. And so now we have this with our carbocation here. And if we continue to move electrons the same way, these will come here. And so our next resonance structure will look like this. Now our carbocation is here. And the last thing that we're going to do is move electrons from this double bond to here. And so now we have essentially the species that we started with, but the double bonds have all switched around inside the aromatic ring. So our carbocation, our positive charge is back on the same carbon that it started on. And all the double bonds in the ring have moved around. Okay, so then for B, we have phenol. And so to begin, one of the lone pairs on the oxygen of phenol can add in here. That's going to cause the electrons of this double bond to move. And so we'll have only one lone pair on this oxygen now, and a positive charge, and this oxygen will have a double bond. And so we will have this, and there's going to be a lone pair and a negative charge on this carbon now. And so sort of similar to the last problem, we're just going to keep moving electrons around this ring. So those electrons go there. The electrons of that double bond will go to the indicated carbon. And so now we have this. And again, a single lone pair on the oxygen and a positive charge, and a lone pair on this carbon now and a negative charge. And we'll just continue to move these the exact same way. And so now our lone pair and negative charge are here. One lone pair and a positive charge on the oxygen. And then lastly, these electrons can go here. That's going to cause this double bond to break, and those electrons will go back to the oxygen. And so now, again, just like in part A, we're sort of back to where we started, but the double bonds in the aromatic ring have all moved around. Okay, and so that's all the resonance structures for A and B. So then on the next page here, we start with C. So we have an unpaired, we have a lone pair of electrons on a carbon here. attached to an aromatic ring. And so we can kind of start this the way that we started B. So the lone pair can add in and form a carbon-carbon double bond, and that's going to cause this double bond to break. And so we'll be here. And now our lone pair and negative charge are seated on this carbon in the ring. And just as we've seen, or just as we saw in part B of this problem, we can now just start moving the lone pair and then breaking a different double bond each time. So these electrons will go here. And so after this, we will be here with our lone pair and negative charge on that carbon to the left in the ring. And so as you can see, there's really two different ways that we can go here. And so the electrons could add in here, and these electrons could revert to this terminal carbon. And if that's the case, then we end up with this structure. So double bond here, and then lone pair and negative charge on the terminal carbon there. And then the other thing that we could have happen is that the lone pair could go the other way. So I'll do that in red, I guess. Why not? So the lone pair could potentially go here instead. So this bond would break, and those electrons would go to this carbon. So we could have our negative charge and our lone pair there, in which case we would have this structure. And then we can, again, sort of get back to where we started by that movement of electrons. And that's going to give us back what we started with. But again, with the pi bonds in the ring all switched around. So the lone pair is back on the carbon on which it started here, but all the bonds in the ring have moved around. Okay. And it looks like I am pretty low on space here. So let me try to move. All right. Oop, that didn't work. All right. There we go. Okay. So part D here, the end of this problem. We are starting with a carbocation on a carbon attached to an aromatic ring. And so this is going to start similarly to the way that part A did. So these electrons can go here to form the new double bond. And that's going to give us this resonance structure. And so now our carbocation will be here. And then we can just move electrons around again, just like we did in part A of this problem. And so if we do that, carbocation ends up here. Okay. And then again, we can just continue moving electrons. So these can come here. And so now, again, we have a situation where we can go really either of two ways. And so we can just get these electrons to come back here. And in that case, again, we'll get back what we started with just the double bonds all switched around in the ring. So the blue pathway of electron movement there is going to give us our starting material, but with the double bonds in different positions in the aromatic ring. But if instead the lone pair, one of the lone pairs from the oxygen, if instead that moves like that, then the product that we'll get will be this product. So with a double bond to the oxygen here, and so the oxygen is only going to have one lone pair, and the positive charge will be on the oxygen. And so that's probably a pretty strong resonance structure because it does put a charge on the most electronegative atom in this molecule. Okay, and so those are all of our resonance structures for these four species. Again, parts C and D are right here. Parts A and B are right here. And C and D do sort of follow the same pattern as A and B as far as electron movement. They're just a little bit more complex. And so that's the answer to chapter 16, problem number 33.